back. I want to bring out a little bit of the algebra that we've been hiding behind some of these sequent calculus calculations. An algebra just means someplace where you could write equations, and typically equations will have variables and operations. So let's see what we can do to make some operations show up to make an algebra. Let's start with something straightforward. Suppose that I tell you that in the context gamma, I want to assume A. What could I entail? Well, it's in what I just said. I said assume A. So therefore I can conclude A. This is what's known as a tautology. It's a sentence that's true because you said so. There's no need to explain it. I assumed A was true, so therefore A is true. This is also reminiscent of other things we know in arithmetic steps. For example, suppose that I was talking about numbers and inequalities. I could say that A was less than or equal to A. There's other things I could say, like A equals A. This is what's known as a reflexive law. It's an enormously powerful tool, even though it seems like a triviality. Why is it powerful? Well, because it gets us on the board. When we have the reflexive law, we're starting with something valid. It means that we have a truth somewhere in our storyline. For example, suppose that I have gamma and A entail B. Then I also noticed I had gamma and B entailed C. Is there any conclusion I could draw about the whole system together? Well, I would have gamma together with A entailing B, which is all I need to fill that in for free, and I no longer need to assume it, and therefore I get to C without even using B. Let's try to write that using our equalities and inequalities. So there we have the transitive law written for two types of relation. We have the equal sign, and we have the less than or equal to sign. They both satisfy that same relationship, and it's in the same place that we see for this rule. A entails B, B entails C, means A entails C. It's the relationship of the variables to each other in this relation that gives it the property of being the transitive law. This reminds me of a funny story. When I was a child, my grandfather tried to convince me that the transitive law was not true. I'd like to share his argument with you so that you can see if you can spot the problem. Here's how his argument went. My grandfather was a farmer, and on his farm he had an ass. That ass was brown. He also had a brown cow, and he was fairly convinced that the ass was not a cow. The joke is that he's misusing animals and colors. To say that they're equal is a pretty strong claim. If we reduce an ass to being brown and a cow to being brown, then actually, as colors go, they are the same. Keep in mind, if you don't use the same operation all the way through the transitive law, then that's not a transitive law. It's something unrelated. Now, what does this mean about data? Isn't that where we're headed? Absolutely. Remember our journey to data. So start with logical operators. That gives us introduction to elimination rules. Once we have those, we convert them into data types using introduction eliminations of the program. The program can then be run. So let's convert these into implications. For A to entail A is to say that A implies A. And we can go a step further and convert that into a little program. Remember that our implication becomes a single arrow. That's the type of a function. The function is something we need to provide. So what function would we have between a data type A and A? Well, we don't know what A is. This is true of any entailment, so it's true of any data type A. Well, then that gives us some freedom. If we want to explore what could happen, let's choose the easiest data type out there. Let's suppose it's data with only one term in it, so there's a single A. If there's only a single A and I want to send it somewhere, and there's only one target, I can't fail but to send it back to itself. There's no other choice in town. But that's actually a recipe that'll work on any data type, isn't it? If I have whatever values here, and I just simply replace them with themselves, that will always work. And it's what's known as the identity function. There are two different ways to write the identity in common speech. Some people use ID, some people use the number 1. It doesn't matter as long as you tell people what it does. This function is essential. It seems somewhat trivial, but similar to the reflexive law, it's getting truth on the table. If we start with the identity, we at least have something we can do. What about our transitive law? First, we take A entails B and turn that into the implication A implies B. And then we take the entailment of B to C and make that in B implies C. That results in A implying C. Now that we've created this, what do we have as data types? We have functions. Now, because we assumed that A implied B as part of our premise, that means that someone is going to give us evidence of a function from A to B, a program. Someone will give us that program at the start of our quest. They will also give us a G from B to C, because we assumed there was a reason for B to imply C. So now that we have these two programs, our goal is to come up with a third program, a program that starts with data of type A and ends with data of type C. Can you think of such a function? Composition would do the job. If I start with something in A and I apply the elimination rule of functions, I'll get something in B. Remember, if I have an A to B function and I have a little value, little a of type big A, then f of little a has to have type B. That's the rule of elimination for functions. So if I start from A, I'll end up in B. And if I take that value and use it for G, then I'll end up with a value in C. The result is the program is simply g of f of a. We write that as g little circle f. These are the two elementary steps in type theory that let us write down an algebra based on the properties of entailment turned into properties of data types now. They're also the first demonstration of a category. Before we go into what categories are doing in general, let's look at some of the qualities of this algebra. So here's our first question we could ask. We could simply take our identity function and multiply it, compose it with a function f. What would we expect to have happen? Surprisingly, this is incredibly subtle. The subtlety lies entirely in that symbol. We've said nothing about equality in any of our logic so far. So let's imagine this question. Now there's a huge subtlety here. What does it even mean to say that two functions are equal to something? We'll get to that by simply looking at the known elimination rule. Our rules are that we've encapsulated the actual program, so we don't see it from the outside. The only way to access a function is to apply it to some input. Since that's the only rule we know for functions, then one way to talk about equality is that we put equal inputs in, we should get equal outputs out. So let's see what that would look like. The first thing I do is I apply the rule for composition. Remember, when we compose, we take the outside function and apply it to the inside function. So we now have f of identity function of a. Well, what does the identity function do? It changes nothing. So that turns out to be a. The result is that f composed with 1 at a is equal to f of a. So if we take the only notion of equality to be what we can see from elimination, what's called observational properties, then we will say f composed with 1 is f. If you search around the internet, you'll discover that equality of functions has various types. There's intensional, extensional, and properties like this. We're going to stick to this one for now, where we simply compose and see that the values come out as the same values. We now saw this is our first rule. There's a version of it on the other side as well. When I compose 1 with f, what do I get? Now I see that the identity takes as input f of a, and identities don't change anything. This will be f of a. But now we need to be careful. While everything I've said is true, it's a bit ambiguous. It may look like this number 1 is doing the same thing as that number 1, but not quite. Remember that the value here is in type A, and the value here has type B. So this identity is only about the type A. I should put an A on it. And this one over here is only a type B, so I can put a B on it. I now see that the rules for multiplying by 1 are slightly different than you might expect. There is more than one number 1. There's one number 1 for every type of data. When we multiply on the left, we have to use the input values of f, and when we multiply on the right, we need to use the outputs. So when we multiply f with 1a, a has to be the input type of b. When we do 1 times f, then the b needs to be the output type of f. Both of these now are defined and they give us memorable rules. They don't change any of the values. What about composing 3 or more things? So I've set up our situation to talk about the compositions that we're going to do. Remember, we only compose when the output of the first function matches the input of the second function. So here my first function goes from a to b. I'll call that one f. Then g goes from b to c, and c goes to d via h. There are at least 2 ways that you might think to put these together. One way is you might first compose f with g. And once you've done that, you would compose it with h. But there's another possibility. You might instead compose G with H first, and then precompose that with F. The result is there's two ways to get to the same place. Now, that might be all right. There are certainly many situations where going one way or another has an advantage or a disadvantage. There's no reason these have to be equal. But it turns out that one of the ways to simplify a lot of reasoning is to find situations where it doesn't matter the path we use. We could go on any one of the two paths as long as we get to the same place. If they're equal, we're happy. This allows us to do optimizations or reconfigure how we program. So, when that property is available to us, we want to take advantage of it. And here it is exactly available to us. Let's see how. So here's our claim. We're going to investigate that H composed with the quantity G composed with F is equal to the quantity H composed with G and then composed with F. Notice the order of F, G, and H have not changed. They all occur H, G, and F. It's only the parentheses that have moved. It is absolutely a fallacy to say that F of G is the same as G of F. There are many ways you can see this. The example that I like to use is putting on your socks and your shoes. If you put your socks on and then your shoes, that's very different than putting your shoes on and then your socks. There is no way to swap the order, but we can get rid of the parentheses. So let's see why this is true. Once more, to talk about the equality of two functions, the only thing we're going to take into account is the encapsulated function, which means we're going to access it through its elimination rule. So let's compare the two sides on a common input. This is the application of the left-hand function to the value a. And the way we unfold that is we eliminate the composition rule. But this is a case where there's two compositions, so we have to eliminate them twice. So this one bottoms out at H of G of F of A, which is a lot of data. So what I might do here is I might take the right-hand side and try the very same operations and see how far down it goes. Once more, there's two compositions, and we start with the outermost. Think of factoring these. I factored both of these on the left-hand side here so we can see what's going on. Here, in this outer one, H comes off first, and then we apply G of F. Over here, F comes off to the right, and G of F are used. If I follow this implication, I'm on this one over here. So I have H of G still composed, and then applied to F of A. Nevertheless, if I expand that last composition, I end up at exactly the same place. Those two being equal, it means that these two functions are equal on every single input. From the perspective of observational or extensional equality, these two functions are now considered equal. For everything we could observe, anything we put in, we observe they come out the same. So they're really indistinguishable from that perspective. We've now seen this is a property that looks familiar for numbers as well. This is what's known as the associative law. The associative law and the commutative law are often partnered together, but for composition, they're not both true simultaneously. Composition is associative, but not commutative. Let's recap what we have. Here's the laws all together. When we have a function type, we think of values that start with one data type and map to a new data type. With that rule, we get identities for every single data type that take the values in and do nothing to them. They give them right back. But they are nevertheless functions. For any two given functions, we can compose them, provided that the output of the first matches the input of the second. We compose in a specific order, G composed with F, because this is usually not commutative. It is, however, going to satisfy two nice rules. If you compose with the identity, the right one for each side, you won't change the function. And likewise, you can multiply in it without parentheses. It's an associative operation. These rules are already enough to describe this as a category. In fact, whatever a category will mean, it'll simply mean that it has these rules, some form of identity, some form of composition, and it satisfies this identity rule and this associativity rule. Commutativity is not required. Why do we want a category? I'll remind you that what we want out of a category is an ability to narrow down our sites. We want to think logically about smaller domains where we can make good reasoning about why things work, make a robust model. Once we glue them together, we get more complicated structures. Each of the individual things may not be always functions. We might decide to store other data and use these arrows as relationships between them. That's the advantage of describing something as just how it works rather than what it is. This is a relational description. We simply need to be able to relate them as values 1 through 4, whatever the actual data is. This will be a very powerful tool in modeling really everyday science. Finally, I want to draw your attention to one key and subtle point, usually overlooked but essential for all categories. It's the equal sign. Without it, we can't write some of the properties here. When we are comparing two functions, we simply compare them for whether they eliminated to the same values. That observational comparison, or also known as extensional equality. We are now going to move into other categories where equality might mean something different, something weaker, something that's more scientifically important. We don't necessarily want to compare every single piece of a property. We might want to compare them up to some relaxed equalities. When we do that, we need to verify these rules, and it becomes a fantastic way to make new models of the world around you. We'll see how in some future videos. Until next time. That's how you take care of your chalkboard.